When people ask what topology is exactly, a cliché example of a coffee mug turning into a donut comes up. Although this doesn't exactly capture what topology studies, it does give us an important insight into a very important concept of topology: homomorphisms. Wait, sorry, I misread that. Homeomorphisms. Although calling it a homomorphism might be a bit of a misnomer, since homeomorphisms are more akin to isomorphisms. Before we begin our discussion on homeomorphisms, let's briefly talk about what a topology is exactly. A topology can be defined as a collection tau on a set X, along with a definition that the empty set and the set X must both be contained within the topology, and the union of any subcollection is in the topology, as well as the finite intersection of any subcollection is also contained within our topology. And then, by definition, any set within a topology is considered an open set. There are some more nuances and some more details, but I'll assume that you generally know what a topology is already. As a brief example, this can be thought of as a topology on a set with 3 elements. I'll leave it as an exercise to check that any union or intersection of this collection remains within the topology. As most math majors are well acquainted with, functions allow us to transform one set to another set by some defined operation. Sure, there might be some more technical way to define it, but that's good enough for our case. The same thing can be done between topologies, and we'll talk about what a continuous function is. Let's define a function f from a topology x to a topology y. In order for f to be continuous, that would mean that the inverse of an open setting y is an open setting x. In order to get homeomorphisms, it might make sense to discuss isomorphisms first. We can think of a set with 5 elements, and let's say that we shift each element by 1. This can be considered a function on a set with 5 elements, and we notice that our function is actually invertible. This means that our function is an isomorphism. For example, we can go to the element 4 and notice that it goes back to 3. If instead we were to go to the square of each element mod 5, then we note that we can no longer go backwards, since we would then have multiple elements that end on 4, and we can't definitively say what the inverse of our function would be. We can extend this idea of invertibility to functions between topologies now. The formal definition of a homeomorphism just means that the function f from x to y has an inverse f inverse from y to x, such that both of them are continuous. And this makes a lot of sense for it to be comparable to an isomorphism. Now, to finish off this introduction to homeomorphisms, let's create a homeomorphism from the Cantor set to an infinite product of zeros and ones. The Cantor set can be thought of as taking the line open interval 0 to 1 and then removing the middle 1/3. We can iteratively continue to do this on each segment that exists. There are countless properties of the Cantor set that are very interesting, but we will show that the Cantor set is homeomorphic to the infinite product of zeros and ones, which can be thought of as an infinite string of ones and zeros. Each point on the Cantor set can be described as a sum of powers of 1/3 with coefficients 0 or 2. For example, this point can be described as 2/3 plus 2 over 81. Using this description, we can define a function that takes coefficients of our representation of the point of the Cantor set, and if it's 0, then it remains 0 in our string, and if instead it's 2, then we'll have a 1 in our string. So okay, let's define a function f on a point in the Cantor set, which is uniquely defined by the sum from I equals 1 to infinity of a sub I over 3 to the I, where it takes that point and it sends it to this string. As you'll notice, this string is essentially just zeros and ones, which is what we are looking for in our homeomorphism. Now, let's look at the inverse function. Once we have a string with zeros and ones, we can multiply each character by 2 and sum it with a factor of 1/3 to the power of the index of that character. So here's an example of going from the Cantor set to our string, and here's an example of going from our string to the Cantor set. Since the Cantor set is nowhere dense, each open set can be thought of in this ternary expansion sort of way. Additionally, an open setting or infinite product topology is just any set with an infinite string of zeros or ones. Since this is the case, and by the way we defined our functions, in both directions we would have a continuous function since open sets are being sent to their other open sets. This means that we have actually defined a homeomorphism between the Cantor set and an infinite product of sets with elements 0 and 1. Homeomorphisms obviously go a lot deeper than what I've covered, and there are plenty more that I wish I could talk about. They describe a lot about different topologies and allow us to experiment with topologies in unique ways. I hope this topic was interesting, and I thank you for watching.